Hello everyone, this is Vardhaman and welcome back. In this video, we are going to learn about binary search. Binary search is the application of divide and conquer. Now let's look at the algorithm. The input to the algorithm is a sorted array of an element and an element x. Binary search cannot be applied on unsorted array. To apply binary search, the array should be sorted. The output will be the position of the element x if found, else will return -1. Before looking at the code, let's understand binary search with the help of an example. We have our binary search function, and you can see the input to the function is an array A, I which is the starting index, and J which is the ending index, and element X. We have an array A of 10 elements which are arranged in sorted order. We have to find the position of the element X which is equal to 90. The function will be called with array A, the starting index 1 and ending index 10, and the element 90. The first step will be to find the mid element, which is equal to I plus j by 2. Here this will be equal to 1 plus 10 by 2, which is equal to floor of 5.5, which is equal to 5. Now we will compare the element x with the element which is at the mid position. Here we can see 80 is not equal to 90, but 80 is smaller than 90. Here you can see that all the elements which are on the left side of the mid element are smaller than the mid element. Every element on the left side of 80 is smaller than 80 because the array is sorted and we need to find 90 which is bigger than 80. So we will search on the right side of the array. So we will change the value of I as mid plus 1, which is equal to 6, and j will remain same as 10. Now we will call the binary search function again with the updated value of I and j. So the new value of I is 6 and j is 10. We will again calculate the mid element. So mid will be equal to 6 plus 10 by 2, which is equal to 8. Now we will compare the element at the mid position, which is 150 and x. 150 is not equal to 90, but 150 is greater than 90. You can see we have to find a smaller element than 150. So we will search on the left side because it has all the smaller element which are smaller than 150. So we will keep the value of I as 6 and we will update the value of j as mid minus 1, which is equal to 7. Now we will call the binary search function again with the updated value of I and j. So the new value of I is 6 and j is 7. We will again calculate the mid element. Mid will be equal to 6 plus 7 by 2, which is equal to 6. Now we will compare the element at the mid position and x. So here 90 is equal to 90. We have found our required element, which is at the index 6. So at last we will return the mid value. So this will be our answer. Now let's look at binary search algorithm. Here we have a recursive function that implement binary search. Binary search function take input as array A, starting index I and ending index j and element x. The first if condition inside the function is termination condition. When the value of I is equal to j, then we will compare if the current element, which is A of I, is equal to x. If it is equal to x, then we will return I, else we will return -1 because the element is not present in the array. Now we will come to the else part. Here first we will find the mid element, which is equal to the floor value of I plus j by 2. After we get the value of mid, we will check if the element at the mid position is equal to x. If it is equal to x, then we will return mid. So this is the index of x that we are looking for. If it is not equal to x, if it is greater than or smaller than x, if the middle element is greater than x, then we will recursively call the binary search with a new value of j, which is equal to mid -1. So here we will search the left part of the array from I to mid -1. If x is greater than mid, then we will search the right part of the array from mid plus 1 to j. We will recursively call the right part here. Let's look at the time complexity for binary search algorithm. So inside the function, we first have the termination condition, which is equal to I equal to j. So this is a simple if else statement. So this entire block will take big O of one amount of time. Coming to the else part, finding the mid element will take 1 unit of time. So this part is divide part, where we divide the array based on the mid element. The next statement, to compare the mid element and the x, it will also consume 1 unit of time. Next statement, in which we are dividing the array into two parts and recursively calling the left part. So this will take t n by 2 time, and the else part is also recursively calling the right part, so it will also take t n by 2 time, because here in the both section the array is divided into two parts, one is left and one is right. Here you can see this is a if else statement, so at a time only one function call will take place. So collectively time complexity of this statement can be written as t n by 2, because only one function call will happen at a time. We can write the reconciliation for this algorithm. So Tn will be equal to big O of 1. This is when the first mid element is x, which is the element we are looking for, and it will be equal to Tn by 2 plus c. This is when the mid element is not x and we are calling the function recursively. Here Tn by 2 is conquer time, in which we are calling either the right part of the array or the left part of the array inside the function call. We are not taking 2tn by 2 because these function call are inside if else condition. So at a time only one function call will happen. C is the divide time, which is required to find the mid element. All 1 unit of time can be written as constant c. So we have our recurrence relation Tn equal to Tn by 2 plus c. We can use Master's theorem to solve this recurrence relation. So after solving the recurrence relation using Master's theorem, we got the time complexity is equal to log n. Big O of log n will be the worst case and the average case time complexity, and big O of 1 will be the best case time complexity when the mid element is itself x. Coming to the space complexity, so we are using recursion, and recursion will take stack space to store the function call. Here we are dividing the array into two parts every time. So the number of function call will be log n, and so the space complexity will be log n. In the worst case and average case, and it will be big O of 1 in the best case. Let's also look at the coding implementation of binary search. So here we have our two function, binary search and the main function. Inside the main function, we have declared the array A, element x, and we are calling the function with value A, 0, and minus 1 and x. Now coming to the binary search function, it is taking 4 input, array A, I, j, and x. First, if is a termination condition, this is when the value of I and j will become equal. So we will check if the element is equal to x. If it is equal to x, then we will return the index I, else we will return minus 1. In the else part, we will calculate the mid, and we will check if the current mid element is equal to x. If it is equal to x, then we will return the mid index. If mid element is not equal to x, then we will check if x is greater than or smaller than the mid element. If it is greater than x, then we will recursively call the left subarray, and if it is smaller than x, then we will recursively call the right subarray. Now let's run this program. So we have to find the position of the element x, which is 10. So here the element is present as index 3.